Okay, good afternoon, everyone, and welcome to our afternoon session, our last one of the day. Pleasure to have you all with us, and pleasure to have David giving another presentation on the screen. David is happy to take questions any time. So if you do have a question, if you could please post it in the chat, and David will try and handle them as we go. If the chat starts lighting up and there's a lot, then we'll handle that as we go. But I'm going to hand over to you now, David, if you're ready to go.
Yeah, sounds good.
Perfect. Over to you, David.
Okay. So, yeah, no, thanks for coming. I know it's late in the day. I'm David Hutton. I work on the LSPR these days, like how we rate the box, but a lot of what I'll be talking about here stems from my experience in my past life at IBM, where I worked on the processor design team and performance modeling team. And so this well, I guess we'll just jump right into it. Well, uh, the the title of this is, I'll jump back to the title slide briefly. It's the primer to the IBM Z processor optimization primer. The IBM Z optimization processor optimization primer is a document that's available on the web. It's quite Googleable, but there's also a direct link to it. And when new versions are released, they should all be posted at that same link near the bottom. And what it is, like the genesis of this document came about maybe 15 years ago when I mean we've had Linux running on the platform for over 20 years at this point. But after several years, there was a lot of interest from the Linux community, like people that worked on Power Linux or x86 Linux, and they're coming over to Z Linux, and they wanted like a, they didn't want to read the phone book, thickness of the principles of operations. They wanted the short version of, what are the, for somebody who kind of, already knows computer architecture, what's the Cliff Notes version of the principles of operation for people who would be programming on this system, on System Z. And so that's what this document really is. And while it was written at the behest of the Linux community, there's nothing particularly Linux specific in it. So anybody working on IBM Z, particularly anybody writing assembly, this document is for you. And we try to keep a new version that's paired with every new release of hardware, and just briefly surmise the more interesting new architecture instructions that are available, rather than you having to go and pour over the principles of operations and distill everything. I don't know if you've ever noticed, but the principles of operations can be a bit of a dry read. And so this is intended to be just a more practical summary of Z and what's new to Z. Okay. And even if you're not, a down in the weeds assembly programmer, it has value to high level programmers as well. People, developing in anything that would be compiled. I'm a computer engineer, and it was at the time, I imagine, the schools that still support it, it's still very much kind of a split brain between electrical engineering that focuses on the digital side of design rather than the analog, and it's got a healthy dose of computer science as well. And in my travels, the best coders are the ones that have an understanding, at least a rudimentary understanding of what the hardware is actually doing underneath. And it drives optimizations, and they write more efficient code. And especially on a platform like Z, where efficiency directly translates into real money. So good document. This presentation is intended just to make you aware of it. There's a lot of stuff in here. I'll try and just, I won't go into too much depth on any one of the slides, but I'll just try and fly over and give you an appreciation of what you can find if you click on that link and pour over the doc. And like I say down there at the bottom, the current version 4 is out there at that link today. It's released last year, and it's updated for Z16. I updated this presentation with for Z17, but the document itself has not been updated yet. That's in progress, and it should be available in another month or two when Z17 officially GAs. So, all right, so let's get into it. So, it talks about the very basics of the architecture, such as, it's ever since 2000, so for 25 years now, it's supported 64-bit, and which was the Z900 machine. It's largely I would argue it's actually a super CISC, complex instruction set computing, versus RISC, reduced instruction set computing, with highly capable instructions. This means, a lot of RISC-like architectures have basic loads and stores, and they have register-based arithmetics. Whereas, as you can see down below, Z has these like RX format instructions where they have one operand as a register and another one is a storage-based operand. So you can do an add of a register against storage contents, and you can without having to do a separate load and then a separate arithmetic that only operates on register to register type arithmetics. We have all sorts of branches. You have indirect, where you specify the branch target like you would a storage or an operand address. You have relative branches where you specify a displacement relative to the branch's instruction address to identify the address of the target. And the benefit of those is, since it's a constant value from the instruction text that you add to another known entity, the instruction address of the branch itself, you can resolve these correctly much earlier in the pipeline than one of these indirect branches that you have to wait until much further down in the pipeline to do a full-blown address generation like you would for a load or a store. So again, hint right off the bat, if you can use relative branches, it's almost always more efficient to do so rather than the classic AGEN or indirect type branches. Another super CISC thing that we have going on in Z is the storage to storage operations, instructions like move character, where you specify one operand in storage for like the source location and another operand in storage for the destination, and you can just move byte by byte from the source to the destination. Then you can get into crazier instructions like move character long, where you can move pages or multiple pages. And we'll talk about how those are facilitated on the architecture. All types of more types of floating point and IEEE, binary, decimal, hexadecimal, more than you could shake a stick at. If there's some floating point architecture, we support it most likely on Z. Then on Z13, we added support for SIMD, single instruction multiple data, and that in turn laid the groundwork for a lot of the vector operations that themselves in turn laid the foundation for the matrix operations upon which a lot of the AI applications are, all the inferencing and is based. So it's a state-of-the-art architecture. It's very robust and has powerful instructions and supports a wide variety, everything from 1964 all the way through the latest matrix-based artificial intelligence manipulations of matrix data. again, not going to walk you through all this, but just to give you some flavor of what's in the document and what the architecture is all about. We have what are called these atomic storage operations. Things like if you're manipulating locks, where you'd have two distinct operations that are kind of fused into one single architected instruction, where either both operations complete or none of them complete. And there's a little pseudocode example for the first for the compare and swap discussed right off the bat. We also have load and add, or the LAA family, or immediate and immediate, XOR immediate. Those instructions that anything it's not obvious, I guess, from the name that the latter would be atomic, but what they do is they fetch a storage operation, they modify it, and then they store it back. So it's a fetch and store implicit in those things, and that's they're managed atomically, such that the order is guaranteed, provided the what is it, the there's a facility that guarantees the order of those specific operations. So we also had the transactional memory support, and this is shaded out because it's a rare instance of an architecture that we introduced and we backpedaled on. It's being retired starting on Z17. We had this notion of constrained and unconstrained transactions. The general purpose of transactional memory was to genericize atomic storage operations, where instead of having a handful of architected Z instructions, you could specify your own routine of any number of instructions that you either all wanted them to architecturally complete or none of them. But yeah, this proved to be rather unwieldy when we were, working through the particulars of future designs and how to support it, given all the new stuff that we're looking at. So yeah, we're pulling it out, and so Z17 is the first one where we've started to rescind transactional memory. It will only support constrained transactions, and whatever the follow-on, presumably if it's called Z18, that machine is expected to not support the transactional facility at all. So again, we try not to make a habit out of doing that, but we unfortunately had to in this case. I'll add, I don't have it in here, but it'll go in the document. We added, I guess, as a sort of a consolation prize, there's another instruction called perform locked operation, and we've added a couple more flavors of perform lock operation support, given that to help ease the pain of the loss of transactional memory. So other just robust additions to the architecture in the modern era, runtime instrumentation, so you can do compiler profiling, sniff out which modules are hot or which branches are particularly difficult to predict, etc. We already talked about SIMD and the vector stuff. We'll talk more about the vector stuff later. Guarded storage facility for Java. It's I've heard it referred to as pause less, but it's really less pausing. It just saves you from having to run and then stop when the garbage collection occurs in one big fill swoop. This will stave it out and make it more transparent. Do a little bit over time. Yeah, some of the compression and entropy encoding. I think the order preserving compression was intended for primarily for DB2 indices. That there's a lot of these things everywhere and they're all compressed. And if you want to compare the indices and they're not order preserved, you have to uncompress them and then compare them and then recompress them. If they're order preserved compressed, then you can compare them while they are compressed. So that's tremendous. Entropy encoding is one of these things where it takes it's a longer duration to do the compression, but that's because it's looking at all the the phrases that the compressed phrases that it generates, and it takes the ones that are most common and assigns them the shortest key. So it needs to do it all up front first, and then go and assign the keys. But so it maximizes compression, although it does take a little longer. Again, I don't intend to read all this to you, but it's just to give you an idea of what's called out and highlighted in the document. How we implement some of these instructions. So yeah, some of them are what you might call RISC. I mean, we certainly have basic loads and stores and register-based arithmetics. We have certain more complicated instructions like branch and count. It's doing a couple things. It decrements a register, and then it compares that register against 0, and then conditionally executes a branch, depending on whether or not R1 is 0. So that we would do what we would crack it into 2 micro operations, one to do the decrement and then another one to do the branch. The execute instruction, this thing was designed in the long ago, so that the length field of move character, the move character instruction didn't need to be modified, which you might have heard of storing into the instruction stream, and this can be very painful for runtime performance, as it requires the pipeline serializes. Particularly with split mode caches, because you can't have the same line in both caches get out of sync. So the synchronization action between the caches when you store into the instruction stream is expensive. Anyway, this was known a long time ago, and the execute instruction allowed a clever way to dynamically modify the length field within the move characters instruction text without directly modifying the instruction text. And that we also split into 2 micro ops, one that fetches the target instruction and another to modify the length field of that target instruction. Load multiples, same idea. We'll expand that into n micro ops, where n is the number of registers that are loaded in the load multiple. So there's still hardware executed. We crack or we break them apart. But then you have some of the crazier instructions, pretty much anything in chapter 10 of the principles of operations, a number of the chapter 7, move character long. I mentioned before is a nice example, where it's like you have to do access exception checking and the page boundaries at the start, at the end, and everywhere in between every time you cross a page. And we have a hardware accelerator that will directly move large chunks of data without necessarily pulling it into the level 1 cache, that we can selectively employ depending on the alignment of the source and the destination addresses. Sometimes if something is maybe you're going to rifle through 100 pages, but the start and the end pages aren't page aligned. Well, maybe we'll do a move character loop to do the fraction of a page and move those bytes. And then once we detect we're at a page boundary, we'll employ this special hardware accelerator to block move the page very efficiently. And then when we get to the end and we determine we have another partial page, we'll go back to another move character loop. And so we'll piecemeal and pick different ways of implementing these various pieces based on the architecture, based on what accelerators are available. And so something like that, it's very difficult to just do that in hardware. So what we have is millicode, where it's basically like a hidden subroutine. It's part of if you hear like ZOS refer to HSA. It's in the HSA. It's a set of routines, and move character long is just one of them. I think there are several hundred millicoded instructions, and but the beauty is you just call move character long and set up the operands, and then under the covers it devolves into this anywhere from several dozen to sometimes several thousand, sometimes 10,000, depending on the instruction. Like it's a routine under the covers that gets called. So again, this is this is maybe the best example of how IBM-Z is what I would call super CISC, super complex instruction set computing. So, quick rundown of the the modern era processor technologies. Going back 15 years to Z11 or Z196. You can really see a lot on this page. We had a 4-core chip in 45 nanometer technology, and you get all the way down to Z17, where it's 16 cores on a dual chip module and 5 nanometer technology. And a couple the super cliff note version of the highlights that went into each of those generations along the way. But each one of those chips is about the same physical size. But we squeeze, this is still, Moore's law isn't dead yet. We're still able to get significantly more transistors into every generation. We can still shrink it. But like I said, 5 nanometers, I mean, 1 nanometer is 10 angstroms. Right. So, we're building transistors that are several atoms, across. Eventually you're going to get it down to the point where if you keep shrinking the technology, you're not going to have transistors. You're just going to have atoms that behave like atoms. So that day is coming when Moore's law will be, no more. But we're not there yet. I think we got a little bit more gas left in the tank. Yeah, there's a lot going on here, but it's a nice handy reference, really. Going down the left, it gives you the short course on the caches from the level 1 out to the level 4 for each of the, from Z196 all the way up to Z17. So you can just compare at a glance big picture items about the caches. And the drawer structure, which is described there verbally. It's also shown topographically at the far right. And then individual drawers are shown kind of in the middle. The second column was intended to explain, like, you see the blue box, which denotes a core boundary and how the caches fall either within or without that core boundary. And this was constructed back around Z13 to show why Z13 had this storing into the instruction stream penalty, unlike any generation that had preceded it. And you can see it really right there in that third box down from the top, that we fully split the level 1 instruction and data caches that are on the processor. So there's no common arbiter on the processor to in case the instruction and data side get out of sync, you now have to go off chip or off core out to the chip level 3 cache for that common arbiter who knows what's in both copies. Previously, there was somebody on the processor chip who was still unified and knew what was going on the instruction side and the data side and could reconcile discrepancies. So it was much faster. And Z13, the penalty was much greater. But for completeness, we carried those graphs forward and showed, like, kind of what Z16 looks like as well. So yeah, just a nice, 15 years of cache evolution and drawer topology evolution. We can we can make this insanely complex, but this is a nice overview of what the processor pipeline looks like. So the top part of this is arranged top to bottom, where you start at the top, you have branch prediction that thinks it knows where it's going in your code, and then it directs the instruction fetcher to fetch a certain address, and then the instruction buffers are presented with a blob of instruction text. And then we start decoding that, where you look at the assembler coders in the room would know that the first thing you do is you look at the first 2 bits of the instruction, which will tell you the length code. Is it 2, 4, or 6 bytes long? And then armed with that information, you can index 2, 4, 6 bytes to get to the start of the next instruction and wash, rinse, repeat. And you do this to find the instruction boundaries. And then you might do that in your first decode stage. And then in your second, you start, bringing the focus into view. Like, all right, well, I have a 2-byte instruction, but is it a branch? Is it, is it a simple arithmetic? What is it? And then, eventually with each stage of decode, you find out more and more about the instruction, like what registers it accesses, what it reads, what it writes, what its dependencies are. And then when you know all that, you can dispatch the instruction to the issue queue for scheduling. And then the scheduler looks at all the dependencies of all the in-flight instructions, and he knows who's dependent upon who. This instruction is going to read general register 5. I know that whoever dispatched 2 cycles before me is going to write general register 5, so this guy has to wait for that guy. But the guy in between him is not dependent on anybody, so he can actually issue out of order, so on and so forth. And then there's like you see like the VFU and the SIMD stuff with all the BFU, DFU boxes and kind of in the middle, and then off to either side of the FXUs and the LSUs. FXU, the fixed point unit. VFU is the floating point unit, with all the sub floating point units, all the different types I mentioned. They each have their own subunit within the parent floating point unit. Fixed point units do the fixed point arithmetic. There's a multiplier and a fixed point division unit attached to one of the fixed point units on either side of the issue queue. We got a load store unit to handle loads and stores, as you might have figured out. So on and so forth. Okay. And then the boxes here are color coded, and there's a little key at the left that says, what went in on what generation. So you can kind of see like the evolution again over the past 15 years from Z196 through present of how that pipeline has evolved. Now the bottom part is even more high level. Like, we don't have any of that detail. We just have color coded groups of related, there's several white boxes for instruction fetch, then like 7 yellow blocks for decode, and then another 7 that are kind of broken up for mapping and wake up an issue. And then at the far right, there's like a longer set of blue boxes at the top, and then a shorter set of 2 at the bottom, after a long rectangular block that kind of unites them both. Yeah, this is a very simplified pipeline diagram, but it's basically the what you see at the top, but if you rotate it counterclockwise 90 degrees and take all the detail out, that's what the bottom is. So it's really like intended to show those 2 big arrows there, the shorter one going across the top and the longer one going across the bottom. These are pipeline hazards. The reject 12, which is about 12 cycles on most of these designs, happens when we miss the cache. Right, and these pipelines are so deep and the cycle time is so short that we have to issue things with the presumption that we think they're going to hit in the cache, and we issue them with that timing, and we issue all dependent instructions against those instructions with this optimal timing. But then when we miss, well, then we got to reject the guy who missed, bring him back all the way back to wake up, and then we also have to chase the tail and bring back everybody that we issued that was dependent upon the guy who rejected, and clean up house. So if you can avoid cache misses, you should. That's the moral of the story of the top arrow. The bottom arrow is the same idea, but a different context and a bigger penalty. That's the branch wrong penalty. So it behooves us to predict our branches as well as we possibly can. Otherwise you have to, a reject, you just have to do a partial pipe flush and a retry. A branch wrong, you have to flush pretty much the entire pipeline and retry from the correct target address. So especially with these high frequency, like around 5 gigahertz designs, with these very deep pipelines, you want to avoid these hazards as much as possible. I neglected to mention back here. Note the clock frequencies over the past 15 years, right? 5.2, 5.5, 5.0, 5.2, 5.2, 5.2, 5.5. So I mean, they've oscillated and or vacillated a bit, but they're hovering all around 5.2-ish gigahertz. Those of you who have been around well before Z196 or Z11 might remember, when we were less than 1 gigahertz, and then we jumped to 1.2 gigahertz and 1.4, and then we jumped up to 4.4 on Z10, and then Z11 jumped up to 5.2. Yeah, those days of like 30%, 40% frequency boosts, they are in the rearview mirror. I think for the rest of our days, we'll be around this 5.2. Again, it might go up a little bit, it might come down a little bit, but it won't overall change significantly from this general 5-ish gigahertz range. But yeah, and that clock frequency bears directly on how many pipeline stages we have, because if you invert the clock frequency, it's the cycle time, and so a very fast frequency inverts into a very tiny cycle time. So and each one of the transistors that it takes to implement all these units and do all that logic, they have real measurable time delays, and the wires have measurable time delays. And if you don't have a lot of time between each of these boxes, each of these pipeline stages, you get there like an automotive factory. Like one stage builds the frame, welds up the frame, another one drops in the powertrain, another one puts the suspension in, and then at the end you have a car. Well, here we do the same thing. We just start with a blob of I-text, and at the end we architecturally checkpoint instructions. But with these fast frequencies, the time we have to do the work in each one of those boxes is very minuscule. So we have very deep pipelines, whereas at the lower frequencies, the pipelines are much shorter. They might have only been like 8 or 9 stages, and now they're well over 20. So again, all that to tie all this together and explain why the hazards are a bigger deal today than they were over 15 years ago. So yeah, I mean, I'm trying to think of how much. I don't want to go into that much detail in all these additional slides. Again, the idea is just to give you a taste of what's out there for you to peruse at your leisure, and you can focus on what interests you specifically. So let's see. We already actually talked about most of the branch predictor. It's kind of its own pipeline that runs asynchronous from the main instruction pipeline, and his job is to he's a history mechanism, just like the caches, right? The caches will retain an address and then the data at that address. The branch history logic will retain branch addresses and target addresses, as well as directional information. Was it taken? Is it not taken? If it varies, probabilistically, is it more likely to be taken than not taken? So on and so forth. So it's a history mechanism, just like the cache. And so he makes his best guess as to where he thinks the program's going, and he will kick off instruction fetches to that end. The main pipeline processes that, believing it as scripture, until either the decode unit or the execution unit, depending if you had an indirect or a relative branch, determines that a mistake was made and the branch predictor, miscomputed or hallucinated where we went versus where we should have gone. So then we do a cleanup action. Yeah, and we talked about dependency management and out of order and all that. But that's all discussed in more detail in the document. If you run profiling and you find that like certain branches you keep stubbing your toe on because for whatever reason they're just nightmarish to reliably predict. Like you see them, they go one direction one time and they go a different direction some other time, and it's not clear what the conditional differences are between going one way one time and another way. Well, you can replace those difficult branches with a load on condition. So what you're doing is here's the pseudocode example over here, and again, like giving you ideas of what you can do to optimize your code what is available in the architecture to facilitate this kind of stuff. Um, so you can replace your difficult to predict conditional branch with this load on condition. So you're swapping a predictable branch that is fast when you predict it correctly, but when you mispredict it, it's very expensive, with a load on condition, which sets a condition code, and then your arithmetic is then dependent on the condition code set by the load on condition. So you're replacing this volatile branch with a more reliable condition code based execution dependency. So yeah, that's an option for difficult branches. But better to be slower overall than be quick on the draw and then have to flush the pipe with significant frequency. There's also these the branch predictor is autonomous, really. He just sits there and he monitors what's going on, and he watches the branches that come over the completion interface. If he made a prediction, he checks to see how his prediction was relative to how it actually resolved, and he squirrels those notes away. Like if he got it right, then he'll say I got it right, and that'll increase the probability that he'll guess the same way for that guy in the future. But it's a learning thing. If you have branches where you'd rather you can directly program the branch predictor to say, here's this branch at this address, it's going here. And that way, when the branch actually presents in your code, there's no learning involved. You've actually directly, educated the branch predictor proactively. So there's no pipe flushes, for the first couple of times for him to get his bearings. So that's another thing you can do, branch wise to try and avoid that deep flush hazard. Cache handling, I mean, again, like philosophically, again, this is all similar because it's all about history mechanisms and what can we do to prime the pump and make sure that these things are there, rather than, like take a demand miss because it's the first time you access something and then have to wait for it. If you know it's coming, we have analogs to, well, I'm kind of jumping ahead because I want to get through this, but you get the idea. We have prefetch data, which is kind of like the analog to the branch prediction preload. If you know you're going to fetch a line and you can tuck this instruction in at some point before then, hopefully that prefetch will go out and you'll take the miss, but you'll hide it because it's ahead of time and it's ahead of when you need it. So those cycles spent waiting for it to come back are effectively hidden. And then, and you may not even make it perfect. I mean, you still might have several cycles exposed, but it's better than having all the cycles exposed. Now, then the question becomes, well, what's the best place to position this? And it's like, well, it depends, man. It's as the bottom bullet says, experimentation is highly recommended. That answer can vary based on the machine generation. It can vary based on the nature of the instructions proximal to the prefetch. For instance, if you have a lot of misses going on, the processor can only support so many misses in parallel at a time. And let's say it's like 6. So that the first 6 misses can allocate a resource to track the miss out to the other layers of cache. If there's a 7th miss, he will have to reject and wait. He'll go back to the issue queue and he will sit there until one of the other 6 frees up his, he gets his data back. He frees up his fetch address register, and then that can be repurposed by the 7th guy. Well, if you have a whole bunch of misses and everything's locked up, your prefetch data will not wait like a normal instruction. We'll just say, swing and a miss. We're not going to stall the pipeline and make, create a bottleneck for a prefetch instruction. It's either ready to go when that thing is ready to issue and he can get his prefetch kicked off, or if everything's pigged up, he's just treated like a no-op. So that's another thing that bears on the equation of where to place this or these instructions. So, but it's there and it's something you can play with. Um, Related, yeah, next instruction access intent. Like if you know you're only going to use something once. Well, let me take a step back. Like the way caches tend to work, you fetch something and it's written into that row of the cache as the most recently used slot, and whoever was the least recently used in that same row gets aged out, and the new guy takes over with his, and he's marked most recently used. And every time another address comes into that same line, that same process happens, and you age out the least recently used and make the new guy the most recently used. Well, what if you're bringing in a line and you're only going to access it once, but you have 16 slots in the row? It's like, well, you have to wait for 15 more accesses to that same line to gracefully age him out. Or you can just directly tell the cache, I'm only using this guy once. You might as well just bring him in as the least recently used guy. So that way he ages out the next time around on one effort instead of the next 15 to demote him all the way out. That's just one example. There are other things that instruction can do, but again, that's the idea. Things that we put in that you can use to improve the performance of your code. Yeah, I mean, this is just general information. Again, there's much more detail provided in the actual document. Yeah, there are things with branch alignment. Yeah, you want to try and maximize, like, if you don't want to start like a new code path near the end of a cache line. It makes sense to kind of start it aligned to the front of the cache line, so that if you don't want to fetch two cache lines when you would only need to fetch one to run a sequence of instructions before the next taken branch. So just basic common sense programming, but I mean it's if you don't know it, you don't know it, and so we try to call that stuff out here too. There's certain things based on how wide the pipeline is, based on how large a group of instructions should be that you would choose to unroll. If you're unrolling prior to Z13 and you have a loop that contains 6 or more instructions, we can the branch predictor will be able to keep pace with that prior to Z13. But starting with Z13, if it contains 12 or more, then the branch predictor can keep up with that. So if you're less than 12, or if you're less than 12 on Z13, you might want to keep it as it is and not unroll it. Actually, I said that bad. You want to unroll for less than 12. You want to, but if it's more than 12, you can let the branch predictor be able to keep up with it. And that answer varies based on the machine generation. So that's all called out. How to manage column returns. Even though we don't have express column returns, we have instructions that we interpret to be call returns. So you don't want to nest them, because that'll trip up the detector mechanism in the hardware, and we tell you what generations of hardware do what in that regard, so on and so forth. Code arrangement, yeah, this is like what's the word for this? I forget what compilers call that. Scheduling of instructions. And there are things about the particular hardware generation, like 3 versus 6, and a notion of side of the issue queue. And if you have things that align on the same side, even if they're dispatched in alternate cycles, they can still bypass to each other. So you might want to put a gap of 3 instructions, to ensure that the ones you want to bypass from and to end up on the same side of the issue queue. Probably more detail than you ever wanted to know, but it's there. If that's your thing, we tell you how to do all this stuff. Or again, if you don't do assembly, this gives you an appreciation for what the compiler is doing, because the compiler knows all this stuff. We send, I was a part of a liaison up to Toronto a couple of times to tell them what we're doing and for them to give us their wish list. And it's one of the beauties of Z is that by owning the stack, we cross collaborate and hopefully do a lot less finger pointing than other computer manufacturing brands who shall remain nameless. What else? Yeah, again, try using NIAI. Details about access pipeline depth that can bear on how you schedule instructions. Common question: how do I clear a large block of storage? And that answer, it depends. How much storage are you clearing? How soon will it be reaccessed? All these things can bear on which type of, do you use move characters in a loop? Do you use XCs, XOR characters? Do you use move long? So on and so forth. I know I'm out of time. I'm pretty much done. But yeah, this was an example of code that one of our clients, again, who shall remain nameless, came at us with, and like, this performs very badly on Z13. And it was probably written in the late 70s. Like it presumes that there's only like 4 floating point registers, and everything that's in red on the left is storage based operand. So there's only like 1 register to register base. Everything else is touching storage. Well, if you get with the times, we did an exact transcription of that into modern instructions that were all register based. And we gave that to the client as a courtesy, and they stopped. They didn't thank us, but they did stop harassing us. But yeah, you can imagine that the speed up was like an order of magnitude. Again, we put this stuff in so that you use it and that you're happy with performant code, and we want you to be happy on the platform. And we see stuff like this at the left all the time, and so. Again, the document is there. Don't be like the company at the left, be like the company on the right. And the document exists to help you be like the company on the right. Yeah, a vector packed decimal facility where we took all the original decimal instructions and they were all storage to storage as well. Like you see down the bottom left, the compare decimal, the 2 storage operands, replaced it with vector based equivalent. So it's register based. So again, a massive speed up taking storage-based expensive operations and converting them into equivalents that use registers. So on and so forth. The AIU, you maybe have been beaten to death, but details about that are in there, as well as updates for Z17. Short list of accelerators and what generation they were added. From that page mover that I was talking about earlier, from way back all the way up to the data processing unit, where we pulled the FICON from our custom integrated circuit from the PCIe adapter cards and stuck it on the Z17 core or processor chip. So handy descriptions of that. And again, like a nice chart showing you by generation. So if you haven't touched your codes in Z10, you're basically foregoing like 40% of the architecture and all these potential optimizations. So that's it. There again, there's the link. Again, this is just to give you a taste of what's out there, and hopefully pique your interest. And by all means, check it out. If you're like, hey, this is great, but I have this question, ship it my way, and I'll add it to the frequently asked questions section. So anything we can do to make it better, by all means, let me know. And that's all I got.
Yeah, thank you, David. I was going to just ask if anybody has any questions. If they do, could they post it in the chat? Whilst you're having a minute to think of your questions and type them out, just to remind people, if they could please submit feedback using the QR code here. And David, would you like to put your email address in the chat so that if people do follow, have any questions later, they can send you an email?
So let's see. I'll sure. It's just hutton@us.ibm.com, but I'll also type it here.
I'm always one of those people who ends the presentation and walks away for 5 minutes and then thinks, "Oh, I should have asked that question," and it comes to me too late.
Oh yeah, I'll think about something when I'm driving home like a day later. Yeah, so
Yeah.
by all means, but yeah, there's again, um,
Oh,
so
wait, sorry, yeah, you sent that to me directly, David. I'll just put it in the chat and send it to everyone. There we go.
and the presentation is up there on the conference page. So
Yes, the slides can be downloaded from the GSC website, like you say. And
yeah,
yeah, great. It doesn't seem that we've got any questions, David. So I'll start bringing it to a close there. I'd just like to say thank you, David, for your time giving this presentation, and thank you for the one earlier as well. It's really appreciated. And thank you everyone who's attended and taken part. Really appreciate you being here. It's the reason we do it and the reason that we organise it. And yeah, if you have any questions that you come up with later, then please do email David and send them to him. Like you said, he's happy to help.
yeah, no, I very much appreciate the interest. So
Great stuff. Okay, well, we'll wrap it up there. Just say thank you again, David, and thank you everyone for attending. Hope to see you all in November. Okay, thank you, everyone.
sounds good. Take care. Bye bye.
Thank you. Bye.